In Chapter 10, we'll be covering the reactions of alcohols, amines, ethers, and epoxides. We'll skip section 10.9 and we'll go ahead and do the homework problems 1 through 18. Now, when we're talking about these different kinds of functional groups, their reaction mechanisms are really the same as we've learned for the alkyl halides. That is, we have an SN1 mechanism and an SN2 mechanism. We have an E1 mechanism and an E2 mechanism. And so these things really happen in the same fashion that you've already learned. So hopefully you've got a good grip on that, having finished up Chapter 9. And what we'll do is we'll start with alcohols, and we'll look at all the mechanisms that occur within alcohols, and then those same mechanisms and how they occur in alcohols also occurs in amines and ethers and epoxides. So let's go ahead and get started with the nomenclature of alcohols. So first of all, we classify alcohols the same way we classify alkyl halides. That is, if you have a group, the functional group, attached to a carbon with only one carbon attached to it, this is known as a primary alcohol. Now, if the carbon has two alkyl substituents on it, then we would call that a secondary alcohol, and a tertiary alcohol has three groups on it. And if you remember when we talked about alkyl halides, the common names for alkyl halides were generated simply by naming the functional group, or naming the alkyl group, okay? And then you follow it with the word in the alkyl halides with bromide or chloride, and now you'll just use the word alcohol. So we have cyclohexane, so that becomes cyclohexyl. So you just get rid of the ANE ending, end it with the substituent ending, and then just call it alcohol at the end. Isopropyl alcohol would have three carbons, right, and connected in the central carbon. Now, what would you call this? I'll draw one for you. And let's see if you can find the common name, and this is where you would pause and try to remember what this alkyl group is called, and then give it the common name for that alcohol. Okay, so this is a T-butyl group. So this becomes T-butyl alcohol. This would be CH3CH2OH. This would be ethyl alcohol. And so forth. You just name the alkyl substituent, and then you add the word alcohol. The naming of alcohols follows the same rules that you learned for alkyl halides, with the exception that now the hydroxyl group, the alcohol functional group, takes priority over all other functional groups, so halogens, alkenes, and alkynes. So the hydroxyl group has to be placed on the longest chain. So we're still doing the search for the longest carbon chain. And it's also given the lowest possible number on that chain. So that's your first priority, so to speak, of naming alcohols. So find the longest chain containing the alcohol and give the alcohol functional group, the hydroxyl group, its lowest possible number on that chain. Now, once you've done that, if there's for some reason a tie, let's say it's in the middle of the molecule, then what you do is you give the lowest possible numbers to these other substituents. And then with more than one substituent, you name all the substituents in alphabetical order when you put the name together. So here's an example for naming an alcohol. Now when you look at this, the first thing your eye really gets drawn to is this chain that's shown here. Yeah, and I did figure out how to make the yellow cursor work. So now, That's the longest chain that you see with your eye, but what you need to do when you name an alcohol is find the longest continuous chain that contains the hydroxyl functional group. So that's this group here. So what we'll do is we'll start the numbering from this carbon. 1, 2, 3, 4, 5, and 6. And then this becomes a substituent of the parent chain. So this becomes a propyl group. So it's on the number 2 carbon, so this becomes 2 propyl, and then it's 6 carbons, so it's hexane, right? So, but hex anol. Again, we get rid of the A and E on the A and E ending. We get rid of the E and we replace it with the OL. Okay, like that. I'd like to give you another example, and that would be this one. I'm going to draw it out here. So this is what I'd like you to do is go ahead and try to name this alcohol using the rule we just applied. And then pause your video and go ahead and try to do that, and then I'll work you through the answer for this problem. Okay, so when you're looking at this problem, the first thing that people will often do is say, well, look, the carbon's here at number 2 or 3. So I'm going to count this way. 1, 2, 3, 4, 5, 6. So it's a 6 carbon chain. So it's a 3 hexanol. But if you look at this problem closely, you can start down here too. 1, 2, 3, 4, 5, 6, 7. So now it's a 7 carbon chain. This carbon is not the number 1 carbon. That's just where it's attached. The numbering is according to the longest chain that the hydroxyl group is attached to. So this becomes 1, 2, 3, 4, 5, 6, 7, like that. Now, this becomes, at that point, a 4-ethyl group. And then we have to give the OH a number in the name. So this becomes 4-ethyl. And then there's 2 ways to do this, just as you've seen before for alkenes. You can either put the number in the front for these simple ones, or you put it inside the middle of the name. So this would be a 4 heptanol. Or you can say hep, tan, and then 4 ol, like that. So either one's acceptable. So let's start by naming compound A. First thing you'll have to look for is where is the alcohol attached, and it's on the ring here. And so the first substituent is to the right. So now the alcohol on a ring will always be number 1, and then this will be 2 and 3 because the hydroxyl functional group has priority. It gets the number 1. Now in naming this compound though, this would be a cyclohexanol, remember they replaced the E with the OL, and it would be 2,3-dimethyl cyclohexanol. I'll let you finish that. Now, for the next compound, what we have is again a cyclohexanol, and then we have 2 possibilities. I can number this way 2, 3, or I can number this way 2, 3. The second substituent should get the lowest number, but you'll notice they're both 3 going either clockwise or counterclockwise from the hydroxyl group. So this is a methyl, and this is an ethyl. So the numbering that we choose would be in the direction of the ethyl group since there's a tie. And then this would be 2, 3 ethyl, 3 methyl cyclohexanol. Next, what we want to do is practice drawing alcohols. So we'll look at C, and in C, what you'll notice is that we have a 2-pentanol. And as is always the case when drawing structures, start by drawing the parent chain. So I'm going to go 1, 2, 3, 4, that's 5. and then this would be my OH because it's 2-pentanol. And in the 3 position, I have a bromo group, so that would be 3-bromo-2-pentanol. Now, looking at problem D, 4-methyl-cyclopent N pent 2-enol, we have to decide what the parent is. So this is cyclopent 2-enol. So what does the En mean? Right, the En means it has a double bond. So when you draw this, it would look like this. It's cyclo, so 1, 2, 3, 4, 5, right? Pent for 5. It has an alcohol functional group, which we'll call the 1 position, like that. And then in the 2 position, we have a double bond. So now you could number this in any direction. I'll number it like this. And then the 2 carbon has a double bond on it like that. And then the 4 has a methyl group like that. So that's how you would draw that. Again, identify what the parent is. Look carefully at the name. Like when you see this number 2, that should tell you, well, the N-all, right? N means there's a double bond. OL means it's an alcohol. In a ring, the alcohol doesn't need to have a number associated with it. So you can just put it on number 1 carbon, or it doesn't have a number associated with it in the name. Well, let's look at the reactions of alcohols. The first thing to recognize about alcohols, amines, ethers, and epoxides is that the O in those compounds, or the N in those compounds, is a poor leaving group because they come from strong bases. So hydroxide is a strong base, and so it makes a poor leaving group. We talked about that actually in previous chapters. So if you're thinking about an SN1 reaction or an E1 reaction, it's hard to make this group leave because this is a strong base and it wants to stay attached. Now, in the case of the alkyl halides are the conjugate bases of strong acids, so they're weak bases, and the result is you can easily form carbocations provided that you have a secondary or tertiary carbon. Nucleophilic attacks usually are not successful with alcohols for the same reason. When the nucleophile comes in to attack the carbon containing the hydroxy group, when the hydroxy group were to leave, it would leave as a strong base, and as the result is the equilibrium is really not favored in the forward direction, strongly favored in the leftward direction. So when we have, and this is generally the case, when we have molecules that are unreactive, what we try to do is we modify the leaving group. And if we can modify the leaving group so that it comes off as a good leaving group, then we can make the reaction happen. And for alcohols, amines, epoxides, all these compounds, one of the methods that's commonly used is an acid catalyst. So what does an acid catalyst do for us? And so let me sort of draw it for you on this slide so you see it initially, and then I'll draw out the mechanism better later. Let's say it's HBr as your strong acid. The picks up the H and kicks off the Br, and the result is the formation of a carbocation. And the leaving group, let me draw that out, that gives us this. And when the leaving group leaves, provided you have a secondary or tertiary carbon, it leaves you with R plus H2O. And H2O is a very weak base, and as a result is a good leaving group. In nucleophilic reactions, the same type of behavior is observed. First we protonate, so there would be a step before here. The nucleophile attacks, and then instead of leaving as OH, it leaves as H2O. So let's look at a couple of examples. Here's a reaction of cyclohexanol with hydroiodic acid. That's the acid that we're using to protonate. If we're using HI, HCl, HBr, what you end up getting is substitution. So this is an SN1 or SN2 reaction where the iodide substitutes for the hydroxide, and you'll notice that the other product that's out here is water. For 1-propanol, we can use something like HCl or HBr. Um, and again, we protonate the oxygen. It leaves as water, and we get a substitution of the halogen for the hydroxy group of the alcohol. Now, this reaction on a primary alcohol is always an SN2 reaction, and this one in particular requires a little bit of heat for it to take place. So let's look at the mechanism, and we'll look at it with T-butyl alcohol. Secondary and tertiary alcohols undergo SN1 reaction mechanisms. You can protonate. The arrow goes like this, right? And now I have the formation of this protonated um, alcohol, and this bond can break. And in a tertiary or secondary alcohol, the carbocation is stable enough that it'll form, and then the nucleophile can come in and attack. Now, it also turns out in this reaction, it is also possible to get an elimination reaction, an E1, so this is the E1 mechanism, where the base, which in this case would be the Br, or more likely another molecule of the alcohol, it can attack and form the double bond, and that's what gives us the structure that's shown over here on the right. Now, here's the deal. When you do substitution reactions of secondary and tertiary alcohols under these acidic conditions, uh, the acid will actually add back to the alkene, and so your final product is actually this. So even though it looks like it's a straight substitution reaction, many times in these reactions you get the same product, but it actually happens as a combination of these two reactions working together to give us one product. Primary alcohols give us similar results, but through a different mechanism. Primary alcohols undergo an SN2 reaction mechanism. The reasons for that are the same as alkyl halides. That is, primary carbocations are unstable, and primary alcohols are relatively sterically unhindered. That is, it has two hydrogens here and the one alkyl group, and as a result, it's easy for the nucleophile to attack. So we get the same result from the alkyl halide, the H protonates, the O, and then the Br substitutes. I don't know what happened there. I'll write that again. Br substitutes. So you'll see the first step, the oxygen attacks the H, the Br leaves, so that leaves me with that. And then the second step, the bromide ion comes back and attacks, does the backside SN2 attack, and displaces the water as a product. I don't like writing it on the arrow like that. So writes leaves, the water leaves as a leaving group. And again, it can do this because water is a weak base. So let's look at the elimination reaction. In the elimination reaction, we use an acid catalyst. And just like in substitution reactions, the first step is protonation of the alcohol to make it into a good leaving group, the OH into a good leaving group. So we'll get the acid to protonate, and then the alcohol function, the hydroxy group leaves as H2O. The acid that's typically used for this kind of reaction is sulfuric acid, and it also requires heat to form the double bond. The mechanism is E1, just like it is for SN1 for secondary and tertiary alcohols. We protonate, and then we break this bond to form the carbocation. Oh, sorry, I should have drawn it down there. And they say the loss of water because the water ends up leaving H2O like that. So that's what this means, right? Water ends up leaving the molecule to form a carbocation. Now, once that carbocation forms, the conjugate base of the acid can come in and eliminate the hydrogen in what we call a beta elimination because it's the carbon from it's off coming off the carbon beta to the original functional group. Again, following Zaitsev's rules, we get a more substituted double bond. The slowest part of this reaction, just like it was for alkyl halides, is the breaking of this bond to form the carbocation. Typical outcome of a reaction like this is that a little bit of the less substituted double bond gets formed, and the majority of your product is the more substituted double bond. Now, between cis and trans alkenes, trans is typically the major product of the reaction. So alcohols can undergo elimination or dehydration by two different mechanisms. For secondary and tertiary alcohols, we get E1 elimination, and the relative rate, or the ease, of dehydration follows the same order that we have for the stability of carbocations because during the course of the reaction, a carbocation gets formed. So for tertiary alcohols, which form tertiary carbocations, what we find is those rates are the fastest for E1 elimination. For secondary alcohols, that's the next fastest, and that also follows the E1 mechanism. So even though it's listed here, the E1 mechanism of primary alcohols doesn't occur because primary carbocations are too unstable to form. The result is primary alcohols will undergo a different mechanism, the E2 mechanism, which we'll talk about shortly. So in essence, carbocation stability directly controls the relative rates of reactions of E1 eliminations of alcohols. So here we show the elimination of primary alcohols by the E2 mechanism. The first step is the same as that for all other alcohols, is that you protonate the hydroxy group to create the good leaving group as water. In the second step, or the next step of the reaction, we use the base, conjugate base of the sulfuric acid, to simultaneously eliminate the hydrogen and kick off the water molecule from the structure to directly form the alkene. The next thing to talk about is oxidation of alcohols. So remember, we classify alcohols as primary, as we do here, or secondary. This is the secondary. I don't know why the letters don't line up anymore, the numbers don't line up. And tertiary. It turns out primary alcohols can be converted into aldehydes by oxidation, and secondary alcohols can be converted to ketones. Now, the oxidation reaction is also known as a dehydrogenation reaction because if you look at the structure of the primary alcohol, you'll notice there's three hydrogens here, and in the aldehyde there's only one. So in effect, you've removed H2, and when we add hydrogen to a structure like an alkene, we call that a hydrogenation. So this is often referred to as a dehydrogenation reaction because of the removal of H2. It turns out tertiary alcohols are not able to be oxidized into aldehydes or ketones. Now, there are some common reagents that get used for this process, and I'm down here right now. I'll come back to this top one. Common reagents that are used for this. One of them is chromic acid, and chromic acid is one of the hard ones to pick out because when you use chromic acid, it can be made in solution a number of different ways. For example, it can be made from chromium trioxide and H2SO4, or it can be made from potassium dichromate and H2SO4. And it even has an alias, which is Jones reagent. So it turns out chromic acid, all you really need to know or recognize is you have a chromium and that you have sulfuric acid, or it's listed directly as chromic acid, which is H2CrO4. Okay, so you have the chromium and then some form of sulfuric acid, or you have uh, chromic acid directly, or you list it as Jones reagent. Now, there's another common oxidizing agent, and this is known as pyridinium chlorochromate. It's easier just to remember that this is called PCC at this point. PCC is a weaker oxidizing agent, and it turns out what it does is it converts primary alcohols directly into aldehydes. Now, you're going to be thinking to yourself, well, maybe chromic acid might do the same thing. In fact, chromic acid does do that. It takes a primary alcohol and converts it into an aldehyde. But it turns out because there's water present in this reaction, it'll usually end up converting it over to a carboxylic acid. Now, there's one other, and I don't know why the book doesn't list it, but one other common oxidizing agent, and it's just bleach. It's sodium hypochlorite. Now, it's not the bleach that you find in your like cabinet. It's a slightly stronger version of that same bleach. In fact, you can buy um, in the store sodium hypochlorite bleach solutions of similar concentrations, but they're typically more like industrial concentrations of bleach. Now, give you some example reactions. Secondary alcohol with either chromic acid or PCC or bleach, okay, will produce cyclopentanone. But if you take a primary alcohol and you use chromic acid, the first thing it'll do is convert it into the aldehyde, but this reaction is so fast and so efficient that eventually it just converts it all over to the carboxylic acid. So really there's no way to stop this in the middle. It just goes directly to the carboxylic acid. Now, PCC on the other hand, and one of the reasons why PCC and bleach are probably more popular for a lot of reactions is because you can stop it at the formation of the aldehyde and it doesn't continue on to form the carboxylic acid. So PCC is a little bit more selective and you can stop it after the first oxidation reaction of the alcohol. So what we'll do very briefly is talk about the reactions of amines. For the most part, amines are relatively unreactive. They have very high pKa values. So for example, ammonia's pKa is 36 compared to an alcohol which is 15.7. If you remember, alcohols, OH minus, well, water has 15.7, but OH minus is a very bad leaving group because the base is so strong. Well, NH2, an amide, is much, much stronger base and much, much less reactive. You can protonate it, or you can alkylate it to give it a positive charge, and that actually allows you to do the elimination reactions of amines. We won't cover those here because they actually involve quite a bit more information, but we can let you save that for when you take Chem 28. Actually, that's when you cover it. So, but we also use amines. We encounter them pretty frequently because they're often used as the bases in reactions. So, aniline is an example of an amine base. This is methylamine, and yet if you'll notice, ethylamine and dimethylamine have roughly the same pKa value when they're protonated. But adding alkyl groups tends to make the bases stronger because of the electron donating effects of the alkyl groups on the nitrogen. Aniline is a much weaker base because the electrons get delocalized by resonance. And we talked about that in the delocalizations chapter. Amines tend to be, aromatic amines tend to be less basic because the lone pair is occupied in delocalization in the ring. A couple of amines that I think you are probably familiar with are ones like nicotine, which is the addictive substance um, in cigarettes and tobacco. Um, it includes a tertiary amine, and it also includes this aromatic amine within a aromatic pyridine-like ring. And conine is also a well-known amine because it's found in hemlock, which was taken by Socrates um, back in, I think, about 500 BC, when he was sentenced to death for quote unquote corrupting the youth of Greece, I think, and also what was the other thing? It was oh yeah, he was introducing new gods, and so he got sentenced to death for that and was made to drink hemlock. He apparently drank it as part of a lesson to his students and then quote unquote peacefully died. I don't know if that part's true or not. Now, a couple of other common amines, and the things that amines are known for is their bad smell. So these alkylamines tend to have a really horrible smell, and you can get that from their names, how bad they smell. This diamine has two nitrogens on it, so it's 1,4 butanediamine, is also known as putrescine, and because it smells putrid. And then you can imagine what cadaverine smells like, because cadaver is the word we use for dead bodies, so it is quite awful. Anyways, that's all we have for amines, and now we'll move on into ethers. I did actually want to mention one other thing as I was listening in the edit, and that is how you name amines. And so amines are named similarly to alcohols. So let's say I have this as my amine. This would be 1, 2, 3, and 4. So this would be butane, right? Oops, sorry. Butane. And then you get rid of the E and you just add the word amine. So that's butanamine. And then if you take and you add a substituent to it, the nitrogen will take priority. So, for example, adding a chlorine here, it would just be 2-chlorobutanamine. Now, the one thing that's different about amine nomenclature that we don't see in any other functional group, uh, when you have nitrogen, is really when you see it, is that the nitrogen is treated as a number. So, for example, let me draw this butanamine again, but I'm going to draw a CH3 here and a CH3 here, and then I'm going to put two chloros here, Cl and Cl like that, okay? So again, it's butanamine. That part doesn't change, but now this becomes 3, 3 dichloro, and then you have to tell people where the methyl groups are. So it becomes N, comma, N dimethyl butanamine. So to tell people where the groups are if they're on the nitrogen, you treat the N just like you would a number. So let's do one more example using butanamine, so we don't have to go through all that again. So I have NH2 like that, and then I'm going to get rid of one of those, and I'm going to put CH3 on it. So now it's an N-methyl, and I'm going to put a CH3 here as well. So this becomes, this is 1 and 2, so this becomes a N2 dimethyl butanamine. And that allows you to systematically name most amines. So let's go ahead and now move over to ethers. Ethers also has a slightly different nomenclature. Now, common names are pretty simple. You name the alkyl group and you end with the word ether. This is true for all common names. You end in the name of the functional group. So, methyl ethyl ether. I have an ethyl group here and a methyl group here would be that. And then methyl isopropyl ether, we have two groups like that. Okay, and one's isopropyl and one's methyl, and you just say the substituents, and then you follow it by the word ether. Now, in the IUPAC system, because not everything can be named as a substituted ether, that is, we can't always just say what the alkyl groups are. So in order to do a systematic nomenclature, you have to come up with a name for the functional group, the ether functional group, and that is an oxy group. Okay, so if it's methyl, it becomes a methoxy. If it is propyl, like it is here, right, or ethyl, sorry. So this is methyl. If this is ethyl, it becomes a ethoxy functional group. You treat it just as you would a halide or an alkyl group. It has the same priority as those groups. And you would just number the parent chain and then put them in order. You would number the parent chain in order of increasing um, you would sorry, you would number the parent chain so that the substituents get the lowest possible number. So I'll give you a couple of examples on the top of this slide. Let's say we have this and this, right? So now you have to find the parent. Now for if it's an alkane and it doesn't have like an alcohol or an alkene functional group in it, you just number the parent chain to give the first substituent the lowest possible number. So this would be 1, 2, 3, 4, and 5. Then you would say it's a 2-methoxy and a 3-chloro. So putting this together, it's 3-chloro, 2-methoxy, and then it's an alkane name, so it's pentane. You would see similar kind of work done in naming a compound if it was cyclic. And what I'll do for this one is I'll put an OH here and then an OCH3. So now when you number the parent, then what you have to do is give the functional group the lowest number, the alcohol functional group the lowest number. So that's a 1, and this is 2. So now this becomes 2-methoxycyclopentanol, or sorry, cyclohexanol. Okay, so the nomenclature is done exactly the same way, and you name the substituents that have the oxygen with the oxy ending. Now, ethers will undergo substitution reactions just like alcohols will. The simplest and one of the common ways to do substitution reactions of ethers is to protonate the alcohol functional group. Or sorry, the ether functional group, just like you protonate the alcohol functional group in alcohols. Now, the difference though is when you do the substitution reaction, you end up with two organic products typically. One of them will be the alkyl halide, and the other one will be typically an alcohol that comes from the oxygen originally in the ether. So for example, here's the oxygen of an ether. The alkyl groups are designated as R and R prime. You add the acid, it protonates, and then what you get is a substitution reaction which produces Ri, an alkyl halide, and ROH, an alcohol. So the first step of the mechanism, as we said, involves um, the protonation by the acid. So I'll draw HI out like this, and then this will come and go like that. And now I have a situation where I can form either a carbocation. If you can form a stable carbocation, in other words, if it's secondary or tertiary, it'll most likely undergo uh, an SN1 type reaction where the bond will break. Oops, sorry. Where one of these bonds will break and form a carbocation. Now, the bond that breaks is the one that gives you the most stable carbocation. So if two carbocations could be formed, the one that gives you the most stable carbocation is the one that'll form. On the other hand, if you have two primary carbons attached to the sides of the ether, so for example, let's say I have this. Oops, sorry, that's not a primary on that side. Let's do this like this, primary. There we go, like that. Then what'll happen is this will protonate, and then it'll be an SN2 style reaction where the nucleophile will either attack to this side or it'll attack to that side. Now here's the thing. The side that produces the major product is the side with the least steric hindrance to the carbon connected to the oxygen. In this case, even though the difference isn't much, it'll probably be this side because it lacks this extra group that's over here. So let's look at these in a little bit more detail. So one of the applications of ethers is that they're used or often used as solvents. The reason we're using them as solvents in organic chemistry is because they tend to be relatively unreactive. The only things they really do react with are hydrogen halides, that's what we typically call them, but HX like HCl, HBr, and HI. Those acids will react with ethers through the mechanisms that we saw on the earlier slides in substitution reactions of ethers. But for the most part, they're generally unreactive. So we have tetrahydrofuran. Furan is a 5-membered ring with an oxygen in it. And then there's pyran, which is a 6-membered ring. And dioxin, which is got 2 oxygens in a 6-membered ring. Now, epoxides are a different class, a subclass, or I should say special class of ethers, in that they are relatively reactive, even though they are ethers. And the reason for this is because they have so there's a lot of strain in a 3-membered ring, and so epoxides, even though they're ethers, tend to be reactive because of that additional strain. Now, epoxides have kind of funny names. The common name system, you would just say, for example, propylene oxide. It almost sounds like an alkene um, in the sense as the ENE, but the oxide means the oxygen is bridging 2 adjacent carbons. So ethylene oxide has 2 carbons joined by a bridge of an oxygen. The other way that we can name ethers, there's actually several ways that ethers get names, is to use the epoxy, to use the prefix epoxy to indicate that there's a bridge between the number 1 and number 2 carbons. So this 1,2 epoxy 2-methyl, so this would be the number 2 carbon, so 1, 2, and then the 2-methyl methoxypropane is shown here on the left, and then 1,2 epoxy butane is shown on the right. Then we would call that 2,3 epoxy butane to indicate that it's between the 2 and 3 carbons. Now, we're not going to go over the mechanism, but you need to know the reaction that epoxides can be formed a couple of different ways. One is to use what's known as a peroxy acid, and in a peroxy acid or a per acid, the Lewis structure looks something like this. and it has a peroxide bond, that's what this is, in the middle, and that causes the formation of an epoxide. Epoxides react like other ethers. That is, first step involves the protonation of the oxygen with the hydrogen from it, like a HBr, HI, HCl, something like that. And then the second step is the halogen comes in as a nucleophilic attack. So this is an SN2 style reaction. Now, it can also happen if you have, for example, a solvolysis reaction with an alcohol present in the solution. And so you can form another ether with an alcohol substituent forming from the other side. So again, you can have epoxides react with like HBr, and you can form an alcohol alkyl halide. It's called a halohydrin, and then you can also do it in the presence of an ether, and when in the presence of an alcohol, and when you're done, what you do is you form this ether on this end from the alcohol when it attacks. Before describing the details of this reaction, so I want to give you a sort of a more of an overview of the reactions. So in reactions of epoxides, if it's under acidic conditions, then we treat it as if a carbocation has formed. So if you were looking at this carbon or this carbon, I should say maybe this carbon or this carbon, where would the positive charge be most stable? Well, this is secondary and this is primary, so this would be the more stable position. So as it turns out, when this reaction takes place, then the nucleophile attacks as if there was a positive charge there, and you end up with the substituent on that more substituted carbon. On the other hand, under basic conditions, you can react epoxides with strong bases like methoxide here. What it does is it ends up attacking the opposite side. And we'll talk about that in detail, but in essence, what I want you to remember is under acidic condition, the substituent goes to the more substituted spot, and under basic conditions, the substituent that you're adding, the nucleophile, goes to the less substituted spot. It doesn't have really much to do with steric hindrance like other SN2 reactions have, but it does have more to do with charge in our transition state. So let's talk a little bit about those details. But again, first thing I want you to remember is acidic and basic conditions, it attacks on opposite carbons, and under acidic conditions, it generally reacts according to the position that would have the most stable carbocation. So under basic conditions, what ends up happening is the nucleophile ends up attacking the less substituted side, in part because that side is less sterically hindered, and also because the less substituted side is better at handling negative charge. The more substituted side has an electron donating group over here, and so it's less suitable for the attack of a negative charge. Now, under acidic conditions, what happens is you form a positive charge on the oxygen, and that positive charge transfers more easily to this oxygen because it's more substituted. The result is, even though the nucleophile can add here to the less sterically hindered side or here to the more sterically hindered side, it tends to go towards the more sterically hindered side because of the partial positive charge sharing between the oxygen and this carbon. We can see that sort of in a transition state, and when we talk about what's happening during the course of the reaction, as this bond breaks, the positive charge is transferred towards this carbon here. If the bond were to break on the other side, the positive charge would transfer to this side here. So we have these carbocation type carbons that are distinguished in their stability as the one on the left being more stable, but also is distinguished by the nucleophile in seeing that the positive charge resides more at this position than it does that position. The result is, under acidic condition, the nucleophile will attack the more substituted side and giving you a substituent on the more substituted carbon. In the mechanism, there's a base involved, usually another alcohol molecule that will be involved in this step, and give us our product here. Okay, so that I just bypassed the structure on the left. Under um, negatively charged conditions, under basic conditions, the nucleophile comes in and attacks this less substituted side because as this comes in and it brings a negative charge, the less substituted side is more able to accommodate the negative charge. It is also the less sterically hindered side, and so we see the attack primarily take place at that position. Once the bond breaks and we have the oxide on this side on the more substituted position now, then this guy attacks the hydrogen of probably another solvent molecule somewhere and ends up giving us our product. In this last slide, I just wanted to show you a couple of more examples of epoxide ring openings. And one involves the use of amines. And so you could have a nitrogen which attacks, a primary carbon, and um, is added nucleophilically to the end of a chain to form an amine. Or you could also use, for example, this is known as butyl lithium. Butyl lithium or other carbon nucleophile type reactions. So, for example, like, sorry, my pen wasn't working for some reason. Carbon nucleophile reactions like acetylide reactions, and you can add a carbon and extend the carbon chain using an epoxide ring. So there's a number of different ways epoxides get used in organic chemistry, primarily for joining two parts of molecules together.